Hello and welcome back to our short tutorial in a short tutorial series now related to differential equations. In the last lecture, we discussed why differential equation was so important. And that, the idea of expanding one lecture in explain to you is for you to give the right importance. I try to show to you, I try to convince you how important it is to know the basis of the differential equations. Because we're going to meet them all the time. All the time we're going to have to express mathematically things that we want to show that are happening in a system. And then we needed the differential equations. And today we're going to continue the lecture. We're going to continue in the second lecture, trying to start to show to you what's necessary to solve the differential equation. Then we're going to be able to build up methods of solution and everything. But again, I want to always reinforce, it's important to know how to solve. But for us engineering, it's even more important, or physicists or chemists, it's even more important to know how to build, how to put together the variations that represents a phenomenon. So always I'm going to take examples that will kind of trying to transmit to you what are the concerns that you have to have when you build up a differential equation, when you're trying to represent a mathematical expression that somehow is a truth for your specific problem. Okay, so continuing our tutorial. Well, if we're going to deal with differential equations, we should start by asking the right questions. And, in a tutorial like this, which is only a few lectures, we want to know, and I've been saying many times, you have to know how to formulate an equation. When you are explaining a certain phenomenon, you need to know what should I take into account, what should I consider important to construct the equation. Because sometimes people are so worried about solution of the differential equations that they forget that, to solve you need to have an equation. And to have an equation, of course, in the course, the professor will come and give you an equation in the blackboard. But in real life, you're going to have to construct the equation yourself. And to construct the equation yourself is what you have to acquire some experience and look to the problem and see what are the important variations, what are the important quantities. So, how to formulate an equation is important. Fortunately, mathematics has already considered many possibilities, and there are many even named equations, Cauchy equations, Taylor, Frobenius, many different equations. Confluent, hypergeometric confluent equations. They already have considered equations that they know take into account the main variations, and they work very hard in solving them. And so when you construct an equation and some mathematician already solved it, oh boy, that's the gloria, because we can collect the solution for an important problem, but we were able to construct the equation. So, how to formulate the equation is one of the questions. For engineering special, if it was mathematicians, normally they imagine different equations that may be important. But for engineers and physicists and chemists and biologists, it's important to know how construct. A second thing is how to solve the formulated equation. Of course, once you construct the equation, you cannot stop there, right? Sometimes we do simplifications of the equations we construct. But the second point, which normally is the most important part of courses of differential equations, is how to solve. For engineering, I wanted to stay and to say very clear once more and to reinforce that 1 and 2 are important. Knowing to formulate and knowing to solve are both important. But, you know, one has to come with the other. You know, if you formulate an equation that nobody has even touched, you have to know how to solve. But sometimes, as I said, many mathematicians worry about solving different generic equations that help us a lot. But we have to know, you know, sometimes our equations are particular for us and we have to know how to solve. And in this tutorial, as I said many times, I wanted to help with these both concepts, trying to always enforce how to build up, but of course mainly, because this is what you learn in your courses, is how to solve. How to give you feeling that, okay, well, this is not hard. There are methods that mathematicians develop that helps a lot to come with solutions that give us the quantity that we have interest. So, those are the two things that we have always to have in mind as engineers or physicists, is how to formulate equation, to express some phenomena, and how to solve. During this tutorial, we're going to concentrate more in the second, but always reinforcing the importance of the first. Okay? Okay, very well. Then once we know that, we should somehow start to explain to you a little more about the equations. Up to now, I only spoke generalities. There are several types of equations. You know, you don't imagine it's infinite number. But of course, as always, we try to classify, and we try to put classes of equation. And the first one that we learn, and maybe one of the most important for us, is what they call ordinary differential equations. Ordinary differential equations are an important class of equation that I'm going to try to explain to you what is an ordinary differential equation. You know, and then other types too. We should be able to learn, we should be able to know, and we should be able to developing methods to apply and to have solution. But ordinary differential equations are the most common that come across us in studying phenomena, especially the ones related to biomedical engineering. Then let's start by the ordinary equations, and then we're going to explain that there are others that can exist. Right? So normally when we're going to deal with the differential equation, as I told you before, we are very much interested in quantities that we want to know. You know, I already spoke about pressure in the body, oxygenation, chemical reactions, size of an object. Everything will be turned into differential equations to understand their behavior with the variation of the environment, with the variation of external variables. Normally, to have the right language for dealing with differential equations, we have a quantity, and this quantity depends in a variable. So the independent variable is x. X normally is the independent variable, so we can even write this, so you never forget. Here, you know, x for us is exactly defined as the independent variable. Is something that I want to know something varying with that variable. So it could be like temperature, and I want to know how the pressure of the body, how the fluence of the body, how the transport phenomena possible in the body, how everything goes on as temperature varies. You know, and maybe it's not always like this. Sometimes I can have more than one variable, and that gets out of the scope of the ordinary equations I'm going to show. So normally, as I said, to unify the way to speak about the differential equations, we call y the dependent variable. So we say that y is a variable or a quantity that depends on the x through a function. So we say that I'm trying to understand this quantity, and I know that's depending on the other. There is an interdependence. But it turns out that I don't know who is this quantity or who is this equation. And how this function or this quantity varies when the independent variable varies in certain conditions is one of the things we have, because is one of the knowledge we need to know to build up the differential equation. But actually, most part of the time, we want to know is I have a quantity, and this quantity depends on many things in many different aspects, right? Like I give you an example in the first lecture that the variation of velocity depends on the force you put, and that's depend on time. But it also may depend on the velocity itself, because maybe viscosity present. So you see, when you put together all these conditions, then the final quantity I want to know is how is the velocity of an object varying in some situation. Depends on many things, right? And this many things is what the differential equation puts together. But we have to start by naming things. And here is the quantity. Here's the function that we are interested. And all the rest now will be to put together the conditions that's giving to the problem, the conditions that the system is imposing to me, and let me identify how will be the variation of this function with respect to the independent variable, right? If I'm able to do that, if I'm able to consolidate that in a mathematical expression, I already have given the first step. And the first step is I have an equation now that relates things, relates everything that maybe is supposed to be important, and then with that we can go on. So when I have functions or quantities that depend only on one variable, and this is the heart of the problem, right? Is this function that's depending on a variable. We call these ordinary differential equations. And the ordinary differential equations can be of many, many different types. You know, sometimes what I know is the relation between the first derivative, or how this quantity I'm looking for varies with the variable x. And here is an example. It's depending on it oscillates with this x, represented by a cosine. So this is a specific situation. And then, of course, from here, I would like to know who is y of x that make this expression true. And this is an ordinary equation. You see, ordinary equation can have all types of functions. It can have also different types of order of derivatives or order of variations. So maybe I'm dealing with another phenomenon that says that the second derivative of this quantity that I'm looking for with respect to the variable independent plus 4 times the same quantity is 0 always in life. So this variation is tied to its own value in each moment in a way that when I add up, they give you 0. Again, the big question in solving this equation is who is y of x that make this possible, That is giving the solution for this. If I can get that, I will be able to tell every time a function has this type of dependence, the second derivative plus 4 times the function itself is 0, independent of the value of x. Independent of the value of x. Because a differential equation is, of course, a true statement in a big domain. Sometimes it's not valid for all the domain of the variables, but normally it's specified. It's valid in more than one value of x. Otherwise, I could not even speak about derivative if I have to restrict myself in a single point. There are sometimes single points with special variations of the functions, but the case here is more generic. So you see, here there is the second derivative. Well, there is other expressions that are even more complex, or more complicated, I should say. Complex, something different of complicated. Here is an equation that says that if I take x squared, multiply by the third order derivative of y with respect to x, times the derivative of y with respect to x, plus 2 times the exponential of x, times the second derivative of y with x is 0. This is an expression. It should be valid for any x. Again, what is the y of x for this situation? This is the purpose of solving the differential equation. All these equations I gave to you, they may have a kind of solution, and they are a specific solution, because when somebody built up an equation like this, it was taking account many things, right? It was taking account that this variation may represent some phenomenon. This, but multiplied by this variation, by the simple rate of variation of the function with x, represent another one, and their product is the most important thing, and so on and so on. One thing is clear: to solve differential equations, you have to know how to derivate, right? Derivative is fundamental here, because differential equations, especially the ordinaries, that is the one that we are looking for, this kind of solution that's depending on a single variable. They are very common everywhere, right? And they all here are ordinary differential equation. And you note that there are different orders of derivation. And the order of the derivation normally classifies what we call the order of the ordinary differential equation, right? But you see that somebody worked hard to get to here. This represents something. Once this represents something, I need to find what class of dependence of y with x will provide such a mathematical true expression. So that's how we solve the differential equation. Okay? Well, so if there are differential equations that are ordinary, natural question is, if there is the ordinary, it must be a non-ordinary, right? This is normally. So if there are, or if there is ordinary differential equation, it must be a non-ordinary differential equation. And in fact, there is a class of differential equations that are not like the way I described to you. They are actually dependence. They represent quantities that are dependent in more than one variable. I have to understand the interconnection of two variables that can independently vary. And those are called partial differential equations. The partial differential equations are situations where I'm looking for functions that depending in more than one variable, x and y. Therefore, they are not ordinary in this sense. They are extraordinary because they now can have much more freedom, because I have to know how one independent variable affects the function and the other independent variable affects the function. And then putting together the phenomena I want to be able to create the true mathematical expression. And with that true mathematical expression, I have the differential equation. And normally to differentiate from the total derivative, which is only the d, we put the del. And the del is a way to say, look, be careful. This function depends in more than one variable. So here is a phenomenon that somebody builds up an equation saying, look, I have a quantity that's depending on x and y. And this x and y can be anything. Can be like temperature, can be pressure, can be concentration of oxygen, can be anything you want. Two dependent variables, right? Like in mechanics could be the mass of the gas or the object and the force. It doesn't matter. It can be anything. Could be the motion of an object in x and y. It can be everything, right? There are many examples that you learn already in your basic courses that somehow is a quantity that's associated with two variables. In three-dimensional and two-dimensional motion in mechanics, we are filled with such situations. And there are situations that you can create a mathematical true expression, at least you believe is true, relating the variation of the function with x, relating the variation of the function with y, and creating an expression. Those are the partial differential equations. And they are not ordinary. They are not ordinary because they have this extra fact. The fact that now on the equation that represents those phenomena or those systems, the quantity I am looking for, it can have a variation with x or with y, or with two different variables. Another example, right, is this one. And this is, I put this because sometimes you have what we call, the mixing of the variation. And there is a whole rule of how is that. This is the variation of f with respect to y, and after the variation of all these with respect to x. So you have phenomena that will depend on how one thing depends with the other, and then how this variate, the rate of variation of the function with respect to y depends with the variation with x. So the rate of the rate is the second order derivative. And in partial equations, this can happen. You can have this mixture of variations. There are examples of this in thermodynamics. Thermodynamics is not an area that is good only for physicists and chemistry. Thermodynamics is everything, because thermodynamics is a part of science that relates macroscopic properties with microscopic quantities. And this is what we do all the time, by trying to understand how microscopic variation affects the macroscopic environment, the microscopic aspects. That's why when we get sick from the nail, we had a nail with infection, it may affect my ears, it may affect my whole body, because it's equivalent of things in local positions that affects the overall. And in thermodynamics, it's very common that we have such type of functions, like the pressure of a gas. It's depending on what? What's the dependence of a gas? It's depending on how many variables? We know that's depending on temperature. But that's all? No, depends on the number of particles in your gas. So you see, any thermodynamic relation that's depending on pressure, we'll need to know how is the variation with the two, because pressure, I can vary pressure depending on number or depending on temperature. So anything that's depending on pressure can vary if I vary number or if I vary temperature. So this is what I have. I have a function with two dependents. I have two independent variables that I can vary. If I build up, which is very traditional, like you may already learn some transport phenomena, like fluid flowing, or mass transport, diffusion, or momentum transport, which is viscosity and all that. They normally depend in more than one, and those equations are filled with differential derivatives. So, you see, if I want to look the pressure in the body, I may know that that's depending on the quantity of fluid, depending on temperature, depending on oxygenation, depending on many things. So this will be build-up dependency here. We consider only two variables, but sometimes there are more than two variables that can vary. And that's thermodynamics is built up based on partial differential equations. Almost never we're going to get ordinary differential equations in thermodynamics, because we know that almost all the thermodynamics variables or functions normally depending in two independent variables. And variation of pressure is intrinsically related to variation on the number and variation on the temperature. And normally here is how the pressure depending on the number, and here is how the pressure depending on temperature. Normally all those are equations that you're going to build. So any variation of pressure depending on two factors, it's not ordinary, it's partial. I hope you understand the difference between ordinary differential equation and partial differential equations. They are both important, and they are all somehow, we cannot say that one is more important than the other, but we need to know both. We need to know how to solve both to be able to deal with these differential equations. And even though you need to know both to be able to construct the differential equations, to be able to, as I said in the very beginning, it's very important to know how to construct. And to know how to construct, you have to know what you're dealing with. If you are dealing with quantities that depending more than one variable, their variations cannot be linked to only one variation. Sometimes we fix it or sometimes we take this and say, no. I'm not gonna let the temperature to vary. So sometimes I remove this. I say I fixed the temperature, and I end up by being back. So sometimes it's possible in special conditions to transform partial differential equations in ordinary differential equations, but this only in special conditions. Okay? Now, just before we start the solution of those differential equations, it's nice to tell you that the differential equations, the ordinary differential equations that now will be basically our topic, it has an order. We normally define an order for the differential equation. What is this order? The order of the differential equation is the highest derivative you have in your equation. So when we say that there is an ordinary differential equation with order n, we must have somewhere a derivative of order n of the function with respect to the variable. Okay? So those are defined as different orders of the differential equation. And the order of an ordinary differential equation is not more than the highest derivative you find. So, examples. Here's an example. This is a differential equation. You can almost identify what is for. Is a differential equation, and involves only order 1 of derivative. So it's order 1 differential, ordinary differential equation. Now, if there is a second derivative, then of course there is a second derivative. This is another equation. It's an example, generic example, right? This will be actually like the oscillatory motion, the driven oscillation of a system will have an equation like this. And this is order 2. Why is order 2? Because it has a second derivative here. But could be order 3 if there is a third order derivative. So the order of the differential equation is the order of the derivation. The highest derivation present in your equation determines the order. So here I can have a second order derivative, I could have a first order derivative, but if I have a third order derivative, then this equation is ordinary equation, ordinary differential equation of order 3. So the order of the equation is related to the highest order of the derivative. Please, here is important to mention that you should not confuse linear to nonlinear differential equation. All those equations are linear. They involve different orders, but none of them comes to square. Suppose I put a square here. Let's take it here. Suppose I come here and I say, well, here goes square. Then this is an ordinary equation, nonlinear. Nonlinear is related to the exponent of the rates of the derivatives order. The order is given by the order of the derivative, not. So you can have any order, so you can have derivatives of any order and it's still linear. Now, when things come square, cubic, root square, then it's nonlinear. So we say that a differential equation is a nonlinear differential equation when things like this happens. When besides the derivation, the derivative of any order, it comes to square or to some exponent. So being linear or nonlinear is related to the exponent of this. The linear is when there is no square, nothing, no exponent, no root square or any other exponent. They are all like this. They don't have that kind. They have different orders of derivation, but not things square or cubic or root square or anything like this. So we are dealing mostly in the first part of this tutorial with ordinary differential equations of order n, linear, which means are those examples type that I gave to you, except taking this out, right? So don't make confusion of the order of the differential equation with being linear or not. You can have a high order and still linear, okay? When things start to appear with square, root square of the orders of the derivative, then we have a nonlinear system, right? So this is, we'll be dealing with first, second, or even third order differential equations, depending on the process we are dealing with. Okay. Now, let's consider that we know to assemble it. We know to assemble an equation. Of course, we want to know how to solve it. We said that this tutorial is more of this. But to solve a differential equation, I must alert you that it's not unique. You may have the same equation with different solutions. And it's very important for dealing with differential equations the boundary conditions. The boundary conditions are conditions imposed on the variables, on the functions that must be obeyed. Those are boundary conditions. So boundary conditions are conditions that the equation must obey. The solution of the equation must obey. Or any part of the solution of the equation must obey. And when dealing with the solution of the differential equation, we cannot complete the problem if we don't have the boundary conditions. So it is essential when somebody formulates an equation and you need to solve, what are the boundary conditions? You know, because we're going to get functions, sometimes more than one, and we need to know what is the real solution there. Normally, the boundary conditions involve, for instance, the initial values of the function relate to the variable, conditions in different regions of your space of variables, or regions that are forbidding for the solution to exist. You know, it's very common in physics. We're dealing with solutions that could never be there. And that has to have the right interpretation. Normally you have a local system. I'm dealing with a differential equation, and I'm dealing with the quantity of bloody, or the quantity of red cells in a body in many conditions. And then suddenly I find that this has more cells than the blood itself. That's not a good solution. Something's wrong in there. I didn't put the right boundary conditions. The boundary conditions is fundamental in the solution of the differential equation. Cannot forget that. And there are many information that has to come together with the differential equation, so you'll be able to solve. So solve an equation is to find the function that makes the equation true, including the boundary conditions. Cannot forget this. Solving an equation is to find the function that makes that expression true, a mathematical truth. So I have an equation, and then I find a solution. I have to go back to the equation and see if it's true, that expression. If it obeys that, it's really solution of that equation. But they cannot forget that to have the solution, you must include the boundary conditions, which is extra informations on the equation. You're going to see that solutions of the differential equations sometimes involve integration or separation of variables and things like this. And the boundary conditions are fundamental for that. So, these are not important information we should have. Okay, now that we are ready, we should start the solutions. Of course, the first order differential equations are normally the most simple ones. And that's the one that we're going to start with. And normally, just by doing integration, just by making the inverse of derivative, we are able to solve the equation and get the function that obeys that. So normally the equations of first order, which means derivative of first order, are the simplest to be solved, and we're going to start by that. But there are many, many methods to solve the ordinary equations in general. Variable separations. Sometimes it's nice to change the variable. I'm dealing with x, but sometimes 1 over x is the best. This means variables substitution. Variable separations is, you're going to see that sometimes because here I'm talking about in general, right? Not only for ordinaries. Variable separations, we can put x and y in different places, and then you can separate the function from the variable is possible. And that means variable separations. But there are other important things, because as you learn in the course of series, that almost all functions can be expressed by power series. So sometimes it's easy to suppose that you have a power series representing a function and solve the equation by that. Laplace transformation is also wonderful. Laplace transformation allows us to, in many cases, get good solutions for it. And I'm going to explain to you what is the Laplace transformation and how to get it. And of course, nowadays, numerical methods are very important for solving the equations. Doesn't matter what method we're going to use, and we're going to discuss in this tutorial, we need always get a feeling about the steps I have to follow to solve the equations, right? So any method has steps to be followed. And this is what we're going to try to fix it to you in this tutorial. Okay, let's start with the first order differential equations, ordinary differential equations. So some example, you're going to see that then there is a sequence of steps. Then we go by variable separation, we go by substitution of variables, and normally it's easy to identify what methods you're going to use. Of course, the most powerful one is using power series, which is called Frobenius method or Laplace transformation, or even other transformation if we have time in this tutorial. Well, see you in the next lecture as a continuation of our short tutorial series, now explaining to you about the differential equations. Bye-bye.